Hello, welcome back to another video. Today we're going to be covering how to conduct a two-way ANOVA or a two-way analysis of variance in Jamovi. Now, in this video, we're going to be covering all of the basics that we typically do in this tutorial. So we're going to be covering what a two-way ANOVA is, how to test the assumptions for a two-way ANOVA, how to conduct a two-way ANOVA analysis in Jamovi and interpret the results. But what I really want you to pay attention to in this video is how to conduct and analyze the post hoc tests. Every time I teach one-way ANOVA and two-way ANOVA in my classes and we start talking about post hoc testing, that's where my students tend to have a little bit of a sticking point because it is a little bit more complicated than the things that we have learned previously. So I'm really going to try and break that down for you in this tutorial, how to conduct that post hoc testing in Jamovi and how to interpret those results. So the research question that we're going to be working with today is we want to know if emotion regulation differs based on age, sex, or an interaction effect of those two things. So let's dig into what all of that means. The data is linked in the description below. Go ahead and open that up and work through this with me in Jamovi, and we'll get started. So the first thing I want to cover is what is a two-way ANOVA. So in the last video, we talked about a one-way ANOVA. ANOVA stands for analysis of variance, and the one or two way is referring to the number of independent variables that are included in the model. So in a one-way ANOVA, we have just one independent variable. And then in a two-way ANOVA, we can have two independent variables. And yes, there are 3, 4, etc. way ANOVAs as well. So we're going to be sticking with two-way today. And just like with a one-way ANOVA, each of those independent variables can handle 3 or more groups. Sometimes this type of ANOVA is also referred to as a factorial ANOVA, but a two-way ANOVA is a type of factorial ANOVA that includes 2 independent variables. So once we introduce an additional independent variable, we start to separate up the effects of the ANOVA into main effects and interaction effects. So what are main effects? Main effects are the effect of one independent variable on the dependent variable. So in this situation, what is the effect of age on emotion regulation? And what is the effect of sex on emotion regulation? So each of those, age and sex, are independent variables. And so the main effects are when we look at those variables one at a time. What is the effect of age all by itself on emotion regulation? What is the effect of sex all by itself on emotion regulation? Those are our main effects. Now the two-way ANOVA introduces an additional independent variable, meaning that now we also need to think about the interaction effect. In other words, how do those 2 independent variables have a combined effect on emotion regulation? That's that interaction. And that can also be one of the most difficult things to interpret. That's why I bring it up now and why we'll talk more about it later. So now we have main effects, each independent variable on its own, on the dependent variable, and then interaction effect, the combined effect of those 2 independent variables on the dependent variable. So to give you more of an example here, let's say that emotion regulation declines with age, but maybe only for female participants, while for males, it stays about the same. That would be an example of an interaction effect because there is a combination of the 2 independent variables that is not the same as what they would be if we were looking at them just one at a time. So we're getting new helpful information from understanding that interaction effect. So just like with all of the other analysis that we've talked about, before we can run our ANOVA, we need to check the assumptions in Jamovi and make sure that we have met the assumptions, and that means we can go ahead and move forward with the rest of the analysis, trusting that our results are going to be interpreted accurately. So with a two-way ANOVA, we have our mainstay assumptions that we've been dealing with previously: independence, normality, and homogeneity of variance. Independence is a very important assumption. It states that each of the data points are independent from one another. However, we typically take care of this in the research design and data collection phase of the process. So once we are in Jamovi, we're going to be taking a look specifically at the assumptions of normality, our dependent variable normally distributed in the population, and the assumption of homogeneity of variance, that the variances between the groups are roughly similar. Let's say you've got your data set open here. You're going to go to Analyses and you're going to click on ANOVA and then select ANOVA again. You're going to move over the emotion regulation sum score into the dependent variable box. And then in the fixed factors box, you're going to move over both age and sex into those boxes. Now to check our assumptions, you're going to click on the Assumptions tab, and you're going to select the test for homogeneity of variance and the test for normality. So the test for homogeneity of variance is sometimes also referred to as Levene's test. And this again is taking a look at the variances of the groups and assessing whether or not they are roughly similar. So ideally here, we would get a p-value that is greater than 0.05 or a non-statistically significant p-value because we want for our variances to be similar. If we had a statistically significant p-value here, that would tell us that our variances differ significantly, and that's not what we want. We want them to be similar, so we don't want them to be different, right? But it's a little bit counterintuitive because normally when we see small p-values, we get excited. Not so when we're testing assumptions. So we want our p-value for the homogeneity of variances to be greater than 0.05, and it looks like it is here, which is excellent. So we have met that assumption. And then we can take a look at our assumption of normality. This is called the Shapiro-Wilk test. Same rule applies. We want for the p-value to be greater than 0.05, and it looks like it is. This indicates that our data are indeed normally distributed. So now that we have met both of those assumptions, we can move forward with the rest of our analysis. In the ANOVA dialog, you're going to be selecting partial eta squared for the effect size, and now we can take a look at the output and begin to interpret. So in this ANOVA dialog, you're going to have 3 different lines before your residuals line, whereas before you might have only had 1. So instead of just 1 variable, independent variable, now we have 2, which means we also have an interaction effect. So first, you're going to see the main effect of sex on emotion regulation. You're going to have the sum of squares, degrees of freedom, mean square, F, p-value, and effect size. So lots of information there. And for now, let's focus on p-value and effect size. So we can see that our p-value there is less than 0.001. That indicates that we have a statistically significant main effect of sex on emotion regulation. A person's sex significantly affects their emotion regulation. Okay, cool. If we take a look now at our second main effect of the age, we also can see that that is statistically significant. A person's age group significantly affects their emotion regulation. However, and this is very important, we also have a statistically significant interaction effect. Anytime that we have a statistically significant interaction, we want to interpret that interaction, not the main effects. Because of how interaction effects work, if we interpret the main effects instead of the statistically significant interaction, that interpretation can be flawed. So we want to focus on the statistically significant interaction when we have one, and here we do. So our p-value is again less than 0.001, and our effect size there is 0.124. As a reminder, the effect size for ANOVAs is something called partial eta squared, and we can interpret that as variance explained. So in other words, around 12.4% of the variance and emotion regulation can be explained by the combination of sex and age, which is a moderate effect size. That's that main ANOVA table. But like we've talked about before in other ANOVA videos, whenever we have an ANOVA with more than 2 groups, as we have here, we need to conduct post-hoc testing to localize the effect. So we know that there's a statistically significant difference in the combination of these groups, but we don't know specifically where that difference lies. So post-hoc testing is going to help us uncover which of these combinations of groups are statistically significantly different from the others. You can scroll down into the ANOVA tab and ask to conduct some post-hoc testing. So under post-hoc tests, you're going to move over sex and age so that you are looking at the interaction effect. So there's an option for sex, an option for age, but you'll see one that says sex, and then there's like a little multiplication symbol, and age. That's the one you want to move over. That's taking a look at the interaction effect. Then you're going to select your correction factor. I prefer the Bonferroni correction factor, but if you have a different preference, you can certainly choose that. They're all going to be very similar, and the idea is that they're helping control the type 1 error rate that gets inflated when we run multiple analyses. And then I'm going to also have you select the confidence interval and effect size for this analysis as well. This will give us additional important information when we're taking a look. We scroll down, we've got some more output that we can take a look at here. We've got the post-hoc test, and you're going to see there's quite a bit of comparisons happening here. Under the sex independent variable, we have male and female, and then under the age independent variable, we have young, middle-aged, and old-aged. So we have lots of different pairwise comparisons happening here. So you'll see in this output box, we've got the mean difference, we've got degrees of freedom, we have T, because again, essentially these pairwise comparisons are all just t-tests. And then we have the Bonferroni corrected p-value. So this is going to tell you here which of these pairwise comparisons are statistically significantly different from one another. So this is going to help, again, localize that effect. As you can see here, almost all of them are statistically significantly different from one another. So we're looking for that less than 0.05 threshold, and there is only one pairwise comparison that is greater than 0.05. So all of the rest of them are considered statistically significantly different from one another. Then we also have the Cohen's d effect size for all of those pairwise comparisons. So we can take a look here and see we have quite a few Cohen's d effect sizes that are greater than 0.8, indicating a large effect. Some of them that are quite a bit greater, some that are even, over 3. So not only are these groups statistically significantly different from one another, but the effect of that difference is quite large. Now, it's also really important to take a look at the plots and tables of the means to get an even better understanding of the relationship between the two independent variables in that interaction effect. So what you can do to attain that is go to the estimated marginal means, and you're going to be creating some terms. So you're going to move over sex and then age into the term 1 box. And then you're going to create an additional term, and in that term, you're going to have age and then sex. Now, this isn't required by any means, but I have found this really helpful for myself and for my students in better understanding the plots. What this is going to do is it's going to give you the plot 2 ways, one with the axis one way, and then the next one with the axis flipped. I'll show you what that'll look like. And sometimes this can just help us better understand what's happening with our data. If one plot is a little bit harder to interpret, sometimes if you're just looking at it another way with the axes flipped, for whatever reason, it's easier for you to wrap your head around. So I always like to ask for it both ways. And then another little trick here, so you'll make sure you select plots and tables. But another little trick here is under error bars. Anytime that I'm looking at an interaction effect and I have lots of things going on, I select none for the error bars because it just takes away one thing from the plot and makes it a little bit easier for me to focus on what it is that I want to take a look at. Now we can look at the plots and tables of those estimated marginal means here. So what we're looking for here, we know we have an interaction effect, which means that there is a combined effect of age and sex in a way that is different from what each of the main effects would be on their own. Females compared to males, there is higher emotion regulation scores. However, when we're comparing middle-aged and old-aged males and females, for males, old-aged males have higher emotion regulation compared to middle-aged males. But this pattern is flipped for our female participants. For our female participants, our middle-aged females have higher emotion regulation compared to our old-aged females. So this is an example here of something called a disordinal interaction, where the impact of one of the independent variables on the dependent variable is flipped for the other group. We know that there's an interaction, and this has given us even more information on what is happening with that interaction. Here we have a table of the means that breaks it down instead of visually, just so you can compare the means. Of course, it's still visual, but instead of a plot, it's just a table, so you can take a look at the means that way, and that can be helpful. And then here I've got another way to look at the plot. So I mentioned you can flip the axes and then ask for that additional term, and that can help sometimes with interpretation if the first plot wasn't making as much sense to you. So this plot says the exact same thing as the other plot. It just looks different because the axes are different. So now instead of having male, female here at the bottom, we've got the age group here at the bottom, and then the lines representing the sex differences. So again, we can see that we have the male age group. As we get younger in age, our emotional regulation score is lower, or put differently, the older that we get, if we are male, the better our emotion regulation. And then for the female group, we don't see that same pattern hold. So the best emotion regulation for the female group is in the middle age category instead of in the older age category. So again, both plots saying the same thing, but looking slightly different ways to convey that information, and sometimes that can be helpful to see it both ways. Let's recap because we've covered quite a bit here. First, what is a two-way ANOVA? A two-way ANOVA is a type of analysis of variance that involves two independent variables instead of just one. When we introduce that second independent variable, that means that we also then can take a look at the interactions or the combined effects of those two independent variables. That's wonderful because that can give us really cool and neat information. However, that means that we have to take a little bit of extra care in our post-hoc testing when we have a statistically significant interaction. And sometimes we need to ask Jamovi to give us a bit more output, the plots and the tables of the means to help us understand fully what is going on with our data. So an interaction is telling us that there is a combined effect of the two independent variables. And the plots draw out those means so that we can take a look and see where those means are differing from one another and in what way in particular. A great piece of advice that I received before from a statistics mentor of mine is that you need to hear everything 3 times. Now, that's not totally scientific, but the gist of it is that statistics can be difficult. Interpreting interaction effects can be difficult. And so if you've heard it one time and it's not clicking perfectly, that's okay and that's normal. Give yourself more time to practice. If you want more help or you have follow-up questions, please feel free to ask them below. I'm happy to answer whatever questions that you have. You could also reach out to me at ajoytoteach.com if you want more one-on-one support, and I'm happy to work with you there as well. So take care, everyone, and I'll see you in the next video.